So this is a new problem in the series that I'm planning to do. It's a series of word problems with simple linear equations. And much of the complexity of the problem usually is setting up the right equation. Once the equation is set up, you can easily solve it using standard methods. But sometimes where people or students struggle is setting up the equation. So let's go over this example in careful, insufficient detail so that we understand how to approach such problems. And that's one thing I wanted to emphasize here, that every problem is going to be different, but the underlying methodology is the same, that you have to set up the right equation that helps you solve the problem in an efficient way. So train A is traveling eastwards at a speed of 80 kilometers per hour. Train B is traveling westward at a speed of 100 kilometers per hour. Each train is 750 meters long. How long will it take for them to cross each other? So imagine that there are two trains that are on parallel rail tracks, and one is traveling eastward, the other one is traveling westward. Let's draw a picture that will make this a little clearer. So this is one track A, and this is, let's call it track B. So this is train A traveling on track A. This is the train, is traveling eastwards. So usually north is on the top, so east is to my right. So train A is traveling eastwards at a speed of 80 kilometers per hour. One small note here, that in the US we use miles as the unit of distance, but the standard notation or the scientific notation is meters or kilometers. So I'm going to stick to meters and kilometers. It doesn't matter, these units can be converted to each other, but for the sake of simplicity, it's better to stick to the standard SI units, because there are the conversion factors between meters and kilometers and millimeters are all multiples of 10. So the unit conversions are simple, versus if you use miles and feet, and then the conversion factors are not easy. The units are not standard, so let's stick to standard units. So this is track A. The train A is traveling eastwards at a speed of 80 kilometers per hour. This is track B. I'm overloading notation here. This is train B on track B. This is traveling westwards at a speed of 100 kilometers per hour. And each train is 750 meters long. So this is 750 meters. And this train is also 750 meters. So we want to see how long it will take for the two trains to cross each other. So let's understand what this means in some detail here. So this is what they will look like when they're on parallel tracks, when they're right next to each other, just about to cross each other. This is train A, this is train B. This one is moving to the east and this one is moving to the west. And their, let's say their engines are barely at the same point on this line here. So this is what they start off at. So our clock starts here. This is where they are about to cross each other. Then there will be a point. So let's call this time 0. This is the starting time where their engines are, or the fronts of the train are almost at the same point, and they are about to cross each other. Then in a little bit of time, it'll look like this. This is train A, and this is still moving to the east, and train B, they are overlapping on parallel tracks, and train B is still moving to the left. Let's call it time t1. The actual values of these times are not important, but I'm just conceptually explaining what is happening here. Then and finally there will be a time when this train A, and there is train B here, and these two trains have completely crossed each other. So their tails are at the same point along the track. The train A is moving towards east at what are still 80 kilometers per hour. This train B is moving to the west with 100 kilometers per hour. So that's the final situation. This is, let's call it time t2. So we want to calculate the time it takes for the trains to completely cross each other. The way to solve this problem is to imagine that one of the trains is at rest and the other train is the only one that is moving. So basically this is relative motion. So this is an important concept. Let's give it a name: relative motion, which is in this particular case we are interested in the relative velocity, which means the velocity or the speed of train A with respect to train B, or train of speed B with respect to train A. So if both trains are moving, then the situation can be somewhat complex. So we imagine that one of the trains is at rest and the other train is doing all the moving. Imagine you are sitting on train A. Then you will see that you consider yourself at rest, and train B is approaching you at a faster speed than its normal speed with respect to ground. Or if you consider yourself to be stationary in train B, then you will assume, or you will feel, that the train A is approaching you at a speed that is more than its speed with respect to the ground. Both of these approaches are equivalent, and it doesn't matter which one you pick. So I'm going to imagine that train B is at rest and train A is the one that is moving. So or in other words, we are thinking in terms of a passenger that is sitting on train B. So think in terms of a passenger on train B. Passenger is at rest. With respect to himself, he is at rest, he or she, and train A is doing all the moving. Right. So if train B is at rest, so let's draw the picture again. This will help us. Train A, I'm going to draw them on the same track. They are on parallel tracks. They are not going to collide, but just conceptually, this is train A and train B. This is moving at a speed, let's call it S1. This is moving to the left at a speed of S2. Then if I were to imagine train B is stationary, so that means I'm adding an eastward or a rightward component here to the speed of B, let's call it S2. Then I have to give the same velocity, that means, so I'm doing a plus S2 here to the velocity, so that B's velocity becomes 0. And then for train A, I also have to add plus S2 here, the speed of train 2 in absolute value. I have to add it to train A. Only then the relative velocity of the two trains will be the same. So after these transformations, I know that S1 is 80 kilometers per hour. S2 is 120 kilometers per hour. So this is before transformation. After my transformation, so train B is at rest. Its speed is 0. Imagine it's a platform, it's a train platform. It's not moving. And train A is moving at 80 plus 120. So S1 plus S2 is equal to 200 kilometers. What are the speeds again? Oh, 80 and 100, not 80 and 120. So let's make it 100. It doesn't matter. Did I use 120 somewhere? No, that's fine. This is 100. So this becomes 180 kilometers per hour. Okay. So this now we are in business. So this train B is 750 meter long. The length of the train will not change because you are adding or subtracting any relative velocities. This train A is also 750 meters long, and this train A is moving to the east with a speed of 180 kilometers per hour. And train B is stationary. Train B is not moving. So now we are asking how long will it take for train A to cross the entire length of train B. That means the train A has to cross its own length plus the length of train B. So it has to cross 750 meters, its own length, plus 750 meters, the length of train B, which is 1500 meters. Now we have all the equations or all the parameters in place. So we have a train A, moving at 180 kilometers per hour in the relative to and needs to cross or needs to travel 1500 meters. Let's do this in a slightly different way. I mean, I can just divide velocities, but let's get them into simpler units. So 180 kilometers per hour. This is 180 kilometers per 60 minutes, which is 3 kilometers per minute, which is 3000 meters per minute. So we can just do this by inspection. You have to formally divide, but I can just do this by inspection. So to travel 1500 meters, train A will need 1500 meters. I'm going to do the division with the units, divided by 3000 meters per minute, which is, so this is 2 half minute. So train A, just to remind you, train A is not moving at 3000 meters per minute. It is moving at its own speed, but its speed relative to B. We imagine that train B is at rest, and that's the way to solve this problem. That because whether we do it from the point of view of an observer on train B who is at rest, or on train A, or someone who is standing on the ground, the answer is going to be the same. The time it takes for train A to travel and cross train B is not going to depend upon the point of view of which observer who is making the calculation. So we imagine that train B is at rest, therefore train A is moving at this 180 kilometers per hour. So to cross 1500 meters, which is 1.5 kilometer, it will take half a minute. Let's just make sure that I have not made any calculation errors here. 180 kilometers per 60 minutes, which is 3 kilometers per minute, right? And so to cross 1500 meters, you are going to need half a minute. So that's how we set up this word problem. So given the word problem, it wasn't immediately obvious what we needed to do here. I mean, it's possible that we can approach this problem in a different way. Some people like to equalize their velocities, and there are various approaches of doing that. I mean, you can get used to it. Given that their lengths are equal, some people like to equalize their velocities and see how long it will take for it to cross half the distance and so on. But it's not very easy to generalize it. The standard approach that always works is, imagine one of the trains is at rest and the other train is doing all the moving, and then you are in business. A similar thing that there is a similar problem that you can solve here that we are going to maybe talk briefly about. I don't think I'll make a separate video on it. Is if the two trains are traveling in the same direction. So here the two trains are traveling in opposite directions, so we added their velocities. But if the trains were traveling in the same directions, then you need to subtract the velocities. So usually the way to approach it is, the slower moving train, we assume that it is at rest, and the faster moving train is doing all the moving. Let's just talk about this quickly. So if the trains moving in the same direction, so here we need to subtract velocities. Not add them. And usually it's easier to imagine the slower moving train. You imagine slower moving train as stationary. Imagine this train is stationary, and the faster moving train will move but at a slower speed. And say, for example, in this case, so if train A and B, they're both moving in the same direction, this is moving at 80 kilometers per hour, this is moving to the right with 100 kilometers per hour, then you can imagine that train A is stationary and B is moving at 100 minus 80 kilometers per hour, which is 20 kilometers per hour. So again, you have to cross 1500 meters at this much slower speed of 20 kilometers per hour. If when moving at 180 kilometers per hour it needed half a minute, then moving at 20 kilometers per hour, how much will it need? 9 times as much time, because you're moving 9 times slower. So to cross 1500 meter, you will need not you, train B will need half times 9, which is 4.5 minutes. We are reusing the calculation that we did earlier, so assuming that that calculation is correct, this is also correct. So this train will need 4.5 minutes to cross if they are moving in the same direction, and it will take half a minute if they are moving in opposite directions. Okay, that's about it.